Hello everyone, welcome to the course on signal system. This is lecture 5 and in this lecture we will see some basics of Z transform along with the properties of ROC. So in our last lecture we have completed the Laplace transform and we have seen what is the relationship between the Laplace transform and the continuous time Fourier transform. Also we have seen what are the motivations behind the Laplace transform. So similarly the Z transform will start with the motivation behind the Z transform. So Z transform is basically again a important mathematical tool for the study of discrete time signals. So Z transform, we can see that it is a generalization of the Fourier transform. So the Fourier transform which I am talking here is it's DTFT basically. So discrete time Fourier transform. Later on we will see what is the relationship between the DTFT, discrete time Fourier transform, and Z transform. So, due to the advantage that Z transform is a more generalized form of transform, so Z transform is having a numerous advantages over the DTFT, which is the Fourier transform. So, the first advantage here of the Z transform is that the Z transform exists, the Z transform representation basically exists for some signals that do not have the corresponding Fourier transform representation. So that's why we can say that Z transform have the ability to handle a large class of signals with similarly the second advantage is that the Z transform is a more generalized tool. So basically we are having the additional insight beyond those facilitated by the Fourier transform, means the Z transform can be applied to different various other types of signals for which the Fourier transform was not able to calculate. Now we'll talk about the bilateral Z transform and the unilateral Z transform. So first we'll start with the bilateral. As the name suggests, bilateral means we have the limits. This is the analysis equation x of z. If we have a signal small x, the transform is represented by capital X here. So x of z is a transform for a signal which is x of n. So we have the analysis equation which is summation n equals to minus infinite to infinite xn z raised to power minus n. Now this bilateral stands for because we have the limits, lower limit as minus infinite and the upper limit is plus infinite. Also we have the another equation which basically helps in calculating the inverse Z transform. So this x of n and we have the corresponding Z transform, it is nothing but the Z transform pair. So as we have already seen in case of Laplace transform that the inverse formula we generally don't use because it involves a contour integration. So we basically utilize a different kind of technique which is called as a partial fraction approach. So we use this partial fraction technique to basically find out the inverse Z transform. Now we'll talk about what is the difference between the bilateral and the unilateral Z transform. So bilateral means both sided or two sided, whereas unilateral means only one sided. So unilateral transform basically it basically utilize or it basically uses in solving the linear difference equations with non-zero initial conditions. So what is the difference between unilateral and bilateral is that for bilateral the lower limit is basically minus infinite, whereas for unilateral the lower limit is 0. So most of the time we'll be discussing about the bilateral Z transform, but in the difference while solving the linear difference equation, we'll be using the unilateral Z transform. Now after the difference between unilateral and bilateral, we'll be discussing what is the relationship between the Z transform and DTFT. So if we recall about the relationship between Laplace and the CTFT, so the relationship was that CTFT was a special case of Laplace transform which was evaluated over the imaginary axis. So in a similar way, we can derive the relationship between the Z and DTFT also. So first of all, I will be starting with the equation of DTFT, which is x of omega is summation minus infinite to infinite xn e raised to power minus j omega n. Now for the existence of DTFT, we can say that the sequence xn must be absolutely summable first. Absolutely summable means that we have summation n equals to minus infinite to infinite mod of xn. It must be a finite value. This is basically the absolutely summable. So if we have the Z transform equation as xz, so if we'll substitute z equals to r e raised to power j omega, where we can say that omega is r is basically denotes the radius of a circle. Later on we'll see in case of ROC. So if we'll put z equal to r e raised to power j omega in, let's say, equation number 2, then what happened? To the left we have x r e raised to power j omega summation xn r e raised to power j omega whole raised to power minus n. Now just we want to open this and we have this final equation x of z. So if we can compare the right hand side of this equation, let's say, with our Fourier transform equation which we have seen earlier, let's say this is equation number 1. So we can say that for that the Z transform is nothing but the Fourier transform of this particular quantity, which is xn r raised to power minus n. So again, for the existence of Z transform, we can say that xn r raised to power minus n definitely converges, means the summation of this particular factor must be a finite value. It must be a finite value. So if we'll put r equals to 1, then discrete time Fourier transform means we can say that if r equals to 1, so this right hand side whole quantity is nothing but the DTFT. So we can say that DTFT is a special case of Z transform evaluated over the unit circle. Means this is r and r equals to 1. So it basically denotes the unit circle centered about the origin. So this is a relationship between the DTFT, discrete time Fourier transform, and Z transform. So basically Z transform is a more generalized form of representation, whereas DTFT is a special case of Z transform evaluated on this particular Z mod Z equal to 1 or R equal to 1. So after this relationship, we'll be starting with our first numerical, that we need to find out the Z transform of a signal which is a raised to power n un. So how we can calculate the Z transform? We have x of z summation. Now because of un, we can clearly write down that the summation, the limits of the summation will be from 0 to infinite. A raised to power n, z raised to power minus n, which can be further written as like this. Summation n equal to 0 to infinite, a z inverse whole raised to power n. Now, this summation will converge when we have to basically check when this summation is converged. So, in order to simplify the summation converges for this particular quantity. The magnitude of this particular quantity must be less than 1. So, rearranging the inequality, we observe that mod z is greater than mod of a. So, mod z greater than mod of a, basically we'll see later on that it will represent a circle whose center is at origin, and the region, basically what we are defining here is the region beyond A. So we can say that a raised to power n un, the transform is 1 by 1 minus a z inverse for all mod z greater than mod of a. So mod z greater than mod of a, it basically is a region of convergence. So if this is a circle which is mod z equal to 1, and if it is given that a is real constant, and let's assume that a is greater than 1, so definitely a will be lying somewhere outside this unity circle, and the region which is also known as ROC is outside the outermost pole. We'll see what are the properties of ROC. So as per the definition of ROC is region of convergence, or we can say it's the magnitude of Z, or are for which the Z transform of Xn, or basically the equivalently the DTFT of Xn r raised to power minus n converges. So basically this will helps us in calculating the region of convergence, or it basically helps in calculating the transform if the transform is feasible, if the transform is able to calculate. Next question we have, find the Z transform of the sequence. Now we have this minus e raised to power n u of minus n minus 1. So how can we start? As per the u of minus n minus 1, the limits has to be minus infinite to minus 1, a raised to power n and z raised to power minus n. Now we want to perform a summation from n equal to minus infinite to minus 1, which can be further replaced by, if we substitute n equals to minus n in this particular equation, let's say. So the summation will be from 1 to infinite a raised to power minus n, z raised to power n. So further I can write down, we can rearrange this as a inverse z whole raised to power n. Now we want to perform the summation. So this summation will be possible only when this a inverse z quantity, if it is definitely less than 1, because this is an infinite summation, and if it only converges when this quantity is less than 1. So if we have the condition a inverse z is less than 1, and correspondingly we can have the region which is mod z less than mod of a. So again, if we'll assume that a is basically greater than 1, so a definitely will be lying here and will be making a circle, and the region which we need to shade is inside, because mod z, we have mod z less than mod of a. This is called as the ROC. So we basically made an important point over here, that if the signal is right sided or if the signal is left sided, then the ROC will be, if it is the right side, then ROC will be outside the outermost pole, or if the signal is left sided, then we can say that the ROC will be inside the innermost circle. Later on we'll see what are the properties of ROC, but at this particular moment we'll be able to basically calculate the Z transform for both type of signals along with their region of convergence. So these both the questions are quite important while we are solving the inverse Z transform also. Now we'll talk about the region of convergence. As I have already told you that region of convergence is the magnitude of Z, or equivalently R, for which Z transform of Xn, or equivalently Fourier transform, or basically DTFT of Xn r raised to power minus n converges. So we have the very first property of ROC. The ROC consists of concentric circles centered at the origin in the complex Z plane. So if we talk about the ROC, then we have the circles in Z plane. Next, if Xn has a rational Z transform, then ROC does not contain any pole, and the ROC is bounded by poles or extend to infinity. Clearly, if we are already familiar that ROC does not contain any pole, because at the location of poles, the transform basically approaches towards infinity. So if the transform approaches towards infinity, that must not be a part of ROC. So next point is, if the Xn is of finite duration, then ROC is the entire Z plane except Z equal to 0 or infinity. Let's say we have an example that if x of n is delta n, if Xn is delta n, we are clearly we are able to calculate what is the Z transform. X of Z equals to 1. X of Z equal to 1, and we can say that the ROC is entire Z plane. Similarly, if we have xn equals to delta n plus 1, so we have the z transform as this is z raised to the power 1. So if we can say that if xn is delta n, so xn is a finite duration and absolutely summable quantity, then the ROC is entire z plane, except now we need to see when z equal to infinite, if we'll represent the entire z plane as a part of ROC, then z equal to infinite, if we'll check, then the value of xz will become infinite. So we can say that the ROC here for delta n plus 1 is entire z plane except z equals to infinity or mod z equal to infinity. So these exceptional points we need to check. Similarly, we can have if xn equals to delta n minus 1. So if we calculate the z transform xz, which will be z raised to power minus 1. So again z raised to power minus 1, and since we are talking about the finite duration signal, so the ROC is entire z plane, but if we'll check for z equal to 0, so at z equal to 0, xz basically diverges, xz will become infinite. So entire z plane except z equals to 0. So these points we must take care that which points we need to eliminate or which point we need to add here. So that's why I have put here that except possibility, the origin and infinity, z equal to 0 or z equals to infinity. Next, fourth property of ROC is if xn is right sided. Very important. If xn is right sided and the circle mod z equals to r0 is the part of ROC, then all values of z for which mod z greater than r0 will also be in the ROC, and the ROC contains all points outside the circle. Means that circle which is mod z equals to r0, the ROC will be, if this is r0 point, so definitely the ROC will be outside the outermost circle. Similarly, the similar kind of approach is applied to the left-sided signal also, that if xn is left-sided and mod z equals to r0 is lying in the part of ROC, then for all values which is means for mod z less than r0 and greater than 0 will also be in the ROC, and we need to see whether this mod z equal to 0 is eliminated or not. So at this particular stage we can say that this r0 is a part of mod z equals to r0 is a circle. So definitely we have the region inside the innermost circle. Next, after this right sided and the left sided, we have an example that if xn is a both sided. So for both sided, very important example we have that xn equals to a raised to power mod n. So if a raised to power mod n, which can be further written as xn, if a is positive, it can be written as a raised to power n un plus a raised to power minus n u of minus n minus 1. So we generally break this xn in two types. One is right sided. This is right sided signal, and this one is left sided signal. So our first and second question basically they are based on the same is applied to these signals. So the transform is 1 by 1 minus a z inverse, and here we have minus of 1 minus a z inverse, and here also we have. So so we can say that we have the result a raised to power n un a raised to power n u of minus n minus 1. In a similar fashion, we can calculate the Z transform for u of minus n minus 1. We will be able to calculate. So at this stage, we can say that we have two ROCs. One is for right-sided signal and the another one is for left-sided signal. So after that, we'll be seeing that the ROC will be intersection of both the ROCs. So we are talking about that if Xn is two-sided, then the ROC Z mod Z equal to R naught is in ROC, then ROC will be consist of a ring like this. It will be in the form of a ring centered about the origin. So this is all about the both sided. Now, if Z transform xz of xn is rational and if it is right sided, then the ROC is a region outside the outermost pole. And if xn is causal, it's quite important that if let's say we have an example xn equal to u of n minus 1, u of n minus 1 or un. So basically the transform x of z will be z inverse whole divided by 1 minus z inverse. So if we calculate the ROC for this, so definitely it is a right-sided signal. So the ROC will be mod of z greater than mod of 1. So mod z greater than mod of 1 means if we'll try to plot the ROC, so this is mod 1 and the region which is greater than 1 is a part of ROC. Now we need to see that at z equal to infinite what happened? Does the Z transform converges or not? So if we'll put z equal to infinite, so naturally 1 by infinite is 0. So definitely the ROC contains z equals to infinity. The same is written over here that if xn is causal, then the ROC also includes infinity. This is causal basically. But let's say if we'll assume xn equals to u of n plus 1. So clearly this is non-causal. If it is non-causal, we are also able to calculate the transform which is xz, z divided by 1 minus z inverse. So the ROC will be again mod z greater than mod of 1. But if we'll check for z equal to infinity over here, then at z equal to infinity, xz will become infinity. So that means the ROC is mod z greater than 1 except z equals to infinite. That point we need to eliminate. Similarly, if we talk about the anti-causal, so this is for anti-causal, means if the Z transform xz of xn is rational and xn is left-sided, then the ROC is a region inside the innermost non-zero pole. So if xn is anti-causal, so definitely the ROC includes the origin. So anti-causal means it's opposite of causal, means that if hn equal to 0 for all n greater than 0, that is basically an anti-causal. Whereas causal is hn equal to 0 for all n less than 0. So we can basically utilize these properties to mark the region of convergence for the Z transform. Now we'll have some properties of Z transform. So we'll first start with the linearity property. So linearity means the linear combination of the signal and time domain results in linear combination of signals in Z domain also. So we must be aware that if x1z is having a ROC which is R1 and x2 is having a ROC R2, then the overall ROC will be basically the intersection part of both R1 and R2. Next is, we can say the translation property or shifting in time domain. it is shifting in time domain, x of n minus n naught. So the property is basically z raised to power n naught x of z. Similarly, we can have x of z plus x of n plus n naught also. So the property will be z raised to power plus n naught multiplied by xz. So what happened if we have x of n minus n naught? So basically, due to this z raised to minus n naught, we are basically adding a pole at z equal to 0. So if z equal to 0, basically what happened? It will make this transform infinity at z equal to 0. So R except for the possibility of the addition or deletion of 0. We need to check clearly. If we have plus, so definitely x of n plus n naught. So we have the possibility that the 0 may be added or deleted. With the help of numerical, we can clarify this. Now, a raised to power n xn, this is nothing but we can say scaling in z domain, scaling property also. So we have x of z by a. So z by a, if we can visualize that our new pole will be definitely multiplied by a factor of a. So the ROC will be something previous ROC multiplied by the magnitude of a. Similarly, we have the conjugation property. The time reversal is quite important, that the reversal of the signal in time domain is x of 1 by z. Means again, if xn is, let's say, right sided over here, so x of minus n definitely will be left sided. So there will be two changes in the ROC. First change is that the ROC, if the previous ROC is right sided, so definitely the new ROC will be left sided. This is first change. Now, if the poles of the previous ROC was lying at let's say z equal to a, so new pole will be lying at z equals to 1 by a. So the new ROC will be R inverse. Similarly, we have the upsampling, downsampling. We have the convolution, very important. This convolution property basically helps in evaluating the LTI systems. So convolution in time domain is nothing but the multiplication of their respective Z transforms. So again, what is possible ROC over here? Definitely it is the intersection of both x1z and x2z. Now, this differentiation property, which is very, very important, differentiation in Z domain. So it says that if we have nxn, accordingly we have minus of z d by dz of xz. So by d by dz means if we are differentiating x of z, so basically we are increasing only the number of poles. So it will not affect the location of poles now. So the ROC will be remain same, whatever we have for x of n. After that, the first difference and the accumulation property. We have already seen these properties somewhere in the DTFT. So if there is some difference, just apply the property of difference in shifting in time domain. We are getting a result which is 1 minus z inverse multiplied by x of z, and the ROC will be definitely R. And due to this 1 minus z inverse, we need to see that it must be taken intersection with mod z greater than 0. Similarly, the accumulation property is a bit similar with what we have seen in case of Laplace transform, the integration property. So the result we are getting here is 1 by 1 minus z inverse multiplied by xz. So ROC will be definitely R intersection with mod z greater than 1. So after these properties of Z transform, we are having the properties, we are having the initial value and final value theorem. So initial value theorem and final value theorem, these theorems are very, very helpful in calculating the value of the signal, when n approaches 0 or when n approaches infinity. So if we can remember the theorems which we have seen in case of Laplace transform. So it says that limit t approaches 0, x of t can be written as limit s approaches infinity, s multiplied by x of s. And the final value theorem says that limit t approaches infinity, x of t can be further written as limit s approaches 0 s multiplied by x of s. So first we'll see the initial value theorem. It says that x of 0 will be mapped basically limit z approaches infinity x of z. It's quite simple. But if we'll see the final value theorem, so if we can compare both the theorems in z domain and s domain. So to the left we have limit n approaches infinity xn. Here we have limit t approaches infinity xt. To the right we have limit s approaches 0, means s equal to 0, the z plane is basically mapped onto the unit circle. This is called as a mapping of s plane to z plane. So it can be equivalently represented as mod z or z approaches 1. So limit z approaches 1, z minus 1 multiplied by xz, or it can also be written as 1 minus z inverse multiplied by x of z. After this, we have two important points. What are the conditions for which these two theorems are applicable? So the conditions that first initial and final value theorems are applicable for the causal signals. Means causal signals means we can say because those are the real-time signals, so these theorems are applicable only for the real-time signals. After that, we'll talk about the final value theorem. So final value theorem is basically applied, or if it is meaningful if the poles of xz lying inside the unit circle. Means if it is causal, first point it is causal, and second point, for a causal LTI system or for the causal signals, the poles definitely must be lying inside the unity circle. So means these two important conditions are very, very helpful in basically deciding whether these two theorems are applicable or not. So after the properties of Z transform, we'll see later on how the Z transform can be used to evaluate the inverse of Z transform. After that, we'll see how we can solve the difference equations using unilateral Z transform. So these are the references. Thank you.